Okay, Assalamualaikum and a good afternoon, everyone. So, for this month's what you call departmental seminar, I've sort of offered myself in place of somebody else. So, what I'm going to give is essentially a talk that was given at some conference earlier in the week. So that talk was about computational. The conference was on computational physics and data science. So I was the odd one out. So hopefully this will be much better reception. Okay, let me go to my slides. Because I will not be able to see you. Anyone?
Yep.
I think I already shared. Okay. Right. This talk is actually was asked by Prof. Guru in UCSI. Was mentioning that I should review quantum computing because nobody else, I think, in the conference was talking about that. So, not being totally in quantum computing, it took me quite a while to actually prepare this, and perhaps because of that as well, I'm going to say only qualitative things. Hello. I'm just going to say only qualitative things on the subject. So please bear with me. So if you feel that you want more details, then probably this will not be the talk that you should be listening to. But in any case, now let's go ahead. So see if the thing works. So this is roughly the outline that I'm going to talk about. So essentially, I'm going to survey what has been done in quantum computing so far, only cursorily, okay? Essentially, there will be recalling some of the histories, and then we'll talk a little bit about the ingredients of what's there in quantum computing, how should we think about it. And then I will talk about the scenario in Malaysia. It's good that Dr. Yap is here from UTM. And hopefully, he can correct me if I'm wrong. And then I will talk about the other intent of this survey, essentially to see, okay, where can we find our niche areas? So these are things that was on my mind to give a little bit of a personal flavor to the talk. Otherwise, everything else is going to be, some other people's work. Okay, so let me go on. So perhaps the earliest, I think probably the common thing that people refer to on the earliest mention of quantum computing. Let me see if I can do this. Was a keynote address by Feynman. This was done in 1981. Okay, and then Feynman sort of speculates the possibility of using quantum physics to actually build a machine based on quantum laws, and then one should be able to sort of make discoveries from a physical point of view on quantum system itself. So this was the main idea, and this is very much, perhaps very much the thing that where quantum computer is going to be useful. At least that's what my thoughts are, and hopefully we get to those ideas a little bit at the end. But actually, much earlier than that was, well, not much earlier, roughly about the same time as well. Paul Benioff has already been working on the theoretical foundations. So he was talking about a quantum-based Turing machine. So, and essentially both Feynman and Benioff, they have their influences from other computer scientists at that time. Okay, I think if you read Feynman's keynote address, which was published here, I hope this works. Can you see the pointer? Somebody?
Yeah.
So this is a paper now published inside IGTP. Okay, so in there, Feynman was referring to Fredkin, I think. Yeah, Fredkin, and he's a computer scientist who works on reversible computing. Okay, and this is going to be quite important in a sense because the main idea behind quantum computing is the fact that you use all these unitary operators which are essentially reversible. And Benioff himself was actually influenced by Bennett. Okay, so Bennett was already talking about, Bennett was at IBM here. Okay, and was already looking into things with respect to reversibility of computation. I think probably the historical context at that time was there was a paper by can't remember the name was talking about this information is physical. I can't remember the person who actually wrote that paper. And essentially, there was parts of when you sort of store data and then erase data from your computational programs. They are actually introducing this dissipation of energy, and that makes the computational task being irreversible. That was the context at that time, and then people talk about reversible computing because most of the physical laws that people have, okay, I think Benioff was also doing something with respect to some classical mechanical laws at the time, if I'm not mistaken. And he was actually saying that, okay, you can actually build up some kind of a reversible computers in a way, in some limited way. Okay. So after that was essentially the well, not to say a breakthrough, but it started off a new thing, which is a development made by David Deutsch, who was also talking about Turing machine. Okay, and it was actually, if I'm not mistaken, it was in this paper on this quantum theory, the Church-Turing principle, and used the quantum computer. He actually produced an algorithm which is now known as the Deutsch algorithm. Okay. So essentially, you have a function that takes 0, 1 to 0, 1, okay, and then you're trying to understand the nature of this function, whether it's going to be symmetry or balance. Actually, that was the later version of that. But what happens is that using some kind of superposition law, one could actually find out the answer for this, the nature of this f, by just a single query kind of thing. But really, in a way, this depends on this global property of this binary function. Okay, so that was all in the 1980s and before, and after that, we have this great period in 1990s. Okay, because this is where a lot of things happening with respect to the theory of quantum computing. Okay, first of all, there is the generalization of Deutsch algorithm. So over here instead of your function being oops, okay, it doesn't come out right. Instead of a function being just 0, 1 to 0, 1, here you essentially have a multiple bit kind of function, and you have the same kind of thing. You look at the global property of the function, and one could actually get the nature of this function. I think can't remember precisely the numbers, but it's probably half the time than the one given by the classical algorithm. Okay, so an important development also in the 90s was essentially the quantum teleportation. Now, usually this is only understood in the context of what we call quantum communications rather than quantum computing. But nowadays, people have seen that, okay, you could actually use quantum teleportation inside quantum computing. And this is a recent paper, for example. Let me just see what it is. Okay, it's here. Okay, which is published around, well, it's this year. Okay, and people talk about also teleportation of gates and things like that beforehand. And then we have essentially Simon's algorithm. Normally, this is quite unknown to the popular literature, but it's mentioned over here because Simon's algorithm is the one that influenced Shaw to do Shaw's algorithm. Okay. So what did Peter Shaw do? Well, he was able to find an algorithm that could do prime factorization in polynomial time, and the implication is big. In other words, most of our security in internet transactions, for example, involve algorithms or a crypto system which is dependent on this prime factorization. Okay, and prime factorization, as you see later on, there is a slide. I hope it's there. There's a slide for that saying that, okay, classically, this becomes a difficult thing to do. It's exponential thing. As you factorize larger numbers, it becomes more and more difficult. Okay, and the other thing that happens in the 1990s are going to be Grover's search algorithm. So this is less spectacular compared to Shaw's, but nevertheless, one actually find a quadratic speedup. Okay, this is for the case of unstructured search. So all of these are happening in the 1990s. In fact, these are I would say the probably the beginning of the quantum information boom in some sense. There was another development which I will sort of reserve this until later, which is quantum error correction was actually done also in 1990s. Okay, so we'll say that probably later. Again, I'm not going into details, but just give you some conceptual ideas so that and also the references are there for you to look at. If you want the slides, I can give it to you. Right. So what's the recent history? Okay, what's the new things that people find? Okay, let me just mention first the generalization of Shaw's algorithm. So if Shaw's algorithm is going to be troublesome for one particular crypto system, then you see that most of the crypto system that is available being used are part of what we call finding hidden subgroups in a bigger group. Okay, so and essentially people has already found a few quantum algorithms besides Shaw, and they all actually showed exponential speed up. And these are mostly on a billion subgroups. Okay. For the nanobillion ones, there is no known exponential speed up so far. But this is the one that's going to be interesting if there's any development, because things like graph isomorphism will be part of this what you call hidden subgroup problem. Okay, so if one can actually find an algorithm that does it, then one can achieve a lot of things. Okay, and then that was generalization of Shaw's algorithm. Grover's algorithm has also been what you call adapted to a different types of search algorithms. So this is actually what is called Amplitude amplification algorithm. So that was done by 14 is Brussels here. So all of these are already started to roll more progress. And another type of algorithm, or essentially gives you the so-called the technology behind D-wave quantum computers, which is essentially they are based on what we call the adiabatic optimization, and the machine themselves are called quantum annealers. So essentially, they are looking for some optimization problem of a Hamiltonian, and then essentially try to find this in a rather different way from the ones like what people think in terms of IBM and Google, for example. They use logic gates, but they are not using such what you call such a machine. Okay, and perhaps in a way related to this, because these are actually looking for some kind of Hamiltonian, and perhaps also in a similar way, one can think of the quantum simulation also looks for some dynamical properties through looking at evolution operators. Okay, so this can also be used to actually solve some physical problems, and I believe there are a few papers on this already, not if not many. Okay, because I have limited reading, but I'll try to survey this. Okay, and then of course there's also quantum walks, which is also again based on evolution of the system, where one limits oneself to how you do random walks on graphs, but in a quantum sense. So that means you use again the unitary operators for this evolution of this particle on graphs. Much more recently, I think this is HHL, which is 2009. Again, there was a slightly new development given by Harrow, Hasidim, and Lloyd, which gives you the initials of HHL, which they produce an algorithm, quantum algorithm for solving linear systems of equations. And this probably spurred a lot of new development, because you find that things like whatever you want to solve for linear algebra kind of problems, one would be able to use this type of algorithms. Okay, so including things like machine learning. So you have quantum machine learning, for example, which I didn't bother to look this up, but essentially all of these are involving some kind of matrix equation and solving those. Okay, perhaps a kind of useful thing that people also has found is this idea of, again, based on this linear equation domain in some sense, is the idea of quantum recommendation system. So the idea is perhaps in the future things like social media, for example, might be using this kind of quantum recommendation system. So they get hooked up to some quantum computers in the cloud, and then they will be able to suggest to you, what do you like and things like that, or suggest what kind of things to shop around. Okay, that was actually given by Karanidis and Prakash, okay, in 2017, and initially they thought that they have done some kind of quantum improvement, a quantum advantage kind of thing. But later on, it happens that somebody else did an algorithm sort of inspired by their algorithm, and they have essentially spurred a new development in the classical computing community. So this is essentially what's called quantum-inspired algorithms. So even if you say quantum computing will not be there, no, you have already developments that sort of positive developments with respect to how you think of algorithms. The last one is probably an important one, which is what we call quantum sampling algorithms. So most of the times when you do all the other algorithms, perhaps with the exception of this adiabatic thing, you require some kind of a precise gate-based kind of thing to and essentially when you do that, that you require that the quality of qubits are going to be high in order to run those algorithms. But quantum sampling algorithms doesn't require so good quality qubits to actually run. And this was the base of the development on this quantum supremacy experiments. Oh, the other thing I should highlight, one of the things that probably I've forgotten to mention this, I did mention in the conference, but let me go back to this. When Peter Shaw discovered the algorithm, it was actually a conference paper in 1994. The more formal journal paper actually appeared in 1999. So this gives a kind of an understanding of how things are developing. So it takes years of maturing a kind of idea, and then the other thing is the fact that in the community of computer scientists, one finds sometimes conferences and workshops are very highly regarded compared to, say, physicists. So these are one of those things that probably sometimes we need to see the differences in the culture, research culture involved. Right. So one of the things that Pascal was saying that even though there are no guarantees, given that you have things like quantum-inspired algorithms, there are no guarantees that the quantum algorithms are actually not giving the real quantum advantage. They still see all these developments going to be a positive development, and one needs probably a much more fine-tuned kind of algorithm, just like your quantum sampling algorithm, but with a better purpose, I suppose. Unlike quantum sampling algorithms that doesn't really serve the purpose besides demonstrating quantum supremacy. Okay, so this was the idea of the NISQ. Where did I put that references? Yeah. So this which is something that Prescott proposed that no, in the future one should be working in this with this outlook in mind, that the kind of quantum computers that you're going to see the next decade or so will be a noisy one, and it will be an intermediate scale. I think I have this in the next slide. Okay. In the past, okay, when they first begin, when they have the prototypes of quantum computing, probably the most promising at that time was NMR, because the qubits are actually shielded in the nucleus. So and at that time, this is reference 23, which is in 2001. Okay. They already have actually implemented a 7-qubit Shor's algorithm kind of thing. Okay. Of course, 7-qubit is probably only telling that you can actually factorize 2-digit number or something like that. Okay, so it's not very useful. But no, in terms of what do you call that? Proof of principle, no, that it works. Okay. And then you have this Prescott coined the idea of quantum supremacy. Some people do not like that, but I guess Prescott was actually aiming a much more extreme version of quantum advantage in a way. So it's definite that it's going to be, quantum has more advantage, definite advantage over the classical computing. So there was this quest for quantum supremacy, and in 2019, they did it. Okay, Google with their Sycamore chip claim they have done this sampling problem and showed that okay, they are able to compute something which probably takes a classical computing at that time when they claim it 10,000 years or something like that, and but then IBM refuted that. Okay, so again, one of the things that one probably see is that when someone says that something is better, quantum is better than the classical case, it was the best known classical case. Okay, and that best known classical case is always a moving target. So things will probably not be definite in that sense. And then slightly after that, there was already the group from China who did boson sampling using photons. So this is I'm not sure whether they actually use this setup, but you can see how horrendous their equipments are in a way. And then how sensitive the alignment of this optical devices. Okay, so and that was published in Science. Okay, so you can actually look this up if you want to know more about that. Okay, so let's move on. So that sort of covers the history part. So let's see. Okay, here's what's next. Is probably one should understand there are 3 broad areas of quantum computers. One is known as the quantum simulators. Well, usually it's the analog quantum simulators, because you're actually modeling it on some Hamiltonian, okay, with some the noisy intermediate scale quantum. And then finally, it's a scalable digital fault-tolerant quantum computers, which is not within reach at the moment. And then no, once you have those physical equipments, one should be able to see whether it's working or not. There are a few indicators where one actually look for to assess performance of those quantum computers. One is the number of qubits involved. This would be the early days. We talk, for example, the NMR computer. We talk about 7-qubit NMR quantum computer. Okay, and this is probably the logical qubits. But then sometimes you put more physical qubits in order to make sure that it works. Okay, particularly when you have 2-qubit gates. These are very susceptible to errors. Okay, Dr. Yap might confirm that to me. And then we have the coherence time of the qubits and the qubit connectivity. So these are all metrics required to assess performance. Recently, there is this idea of quantum volume being suggested as a composite metric. And this is actually, okay, I've forgotten to correct this. This is actually used for to assess the IBM quantum computers in the cloud. I was told by Dr. Bahari in UPM that when they try to run Qiskit on different sites of IBM quantum computers, they have this quantum volume as indicators to see whether whether one quantum computer is actually working better than the other one. Okay. So again, what's next is probably the kind of language and tools that one needs to do the programming inside quantum computers. Now, most of the time you see later on we talk about quantum circuits where one actually look at the individual logic gates. These are probably, if you try to compare with classical computers, this would be the level of assembly language. Okay? Because you're really looking at the hardware itself. Language. No, assembly language. So one probably needs a better way of programming in the future. So one looks for high-level language, and this is probably the thing that I wanted to suggest people to take up is to look at ZX calculus. Later on, we'll say a few things about that. And then, of course, we need a practical quantum error corrections. There have been implementation of this. So, and of course, those in the business or more on product kind of thing, then you talk about product-oriented development. This was actually done by Quantum Delta in Holland. Okay, so let me just highlight a few things about the ingredients behind quantum computing. In classical computing, one talk about bits, 0 and 1, and then, of course, a string of them. What's the difference with the case of quantum computing is that one use the idea of qubits. So the qubits themselves could be similar thing like 0 and 1, but they are given by quantum states. And being quantum states, one allows for superposition. And this set of states, the general qubit states, they actually form a continuous what you call set of states compared to the discrete strings of the bit strings of your classical computer. So in a way, it's a much more complicated thing to consider. And in fact, there was we had a quantum information theorist who came to UPM years ago. They say it's not really fair to compare things with classical computers because we have a continuum of states inside your quantum systems. So these are things that I'm more interested in a way. I look at this geometry of states, and but really, okay. So in other words, what people do is normally they just choose special set of states. So this is a diagram pinched from Prescott. You probably don't want to know about the whole Hilbert space. Okay, the whole Hilbert space is large, but you only care about a small portion of the Hilbert space where you can actually do physical operations. Okay, and here I need to highlight what we have done. Okay, so I'm going to put this in. Chong probably don't get embarrassed about it. So even things like 3-qubit states are already hard to classify, okay, because you have all these possible states. So let me show you the other slide. So this is the work of Chong, who did try to classify the different unitary classes of 3-qubit states. Okay, and this these are done mostly by hand, right, Chong? And when he tries to move on to the next level, which is 4 qubits, it was already quite quite complicated calculations to do. So, and probably need to resort to some kind of computer algebra kind of help. Okay. So this is one of the works that is actually that we do. So again, as I said, I'm mostly interested in terms of the geometry of states. Okay, but really, probably when you do quantum computing stuff, you don't need all these ideas. You probably need just a special set of states. Okay. The other work that was done related to the geometry of states was done by my Iranian student Said Maladaudi years ago, and was looking at essentially the topology of the quantum states. So this is the kind of it's a calculation of what they call this is called this is called Euler Characteristic. Okay. And what it's looking at is essentially the space of quantum states modulo the torus, okay, the torus that acts on this. So really, okay, if you think of the local actions of the SU2s, okay, and each SU2 will have U1s in it, okay, the diagonal or the essentially the cut-and-sub algebra of it, okay. So you have this essentially a torus, okay, and he looks at this reduced phase space, and that reduced phase space, even at the level of say a few qubits, is already complicated. So remember, Euler characteristic is telling you about the number of holes inside the space. So here is the case of the 4 qubits. I think for the case of 3 qubits, it's not shown here because 3 qubits will have Euler characteristics of 8. Okay, so when you go to 4 qubits, already Euler characteristic of 64, and you can see, for example, in the case of the 8 qubits, for example, it's horrendous, and this is essentially the kind of space. This is essentially your the Poincare polynomial. Okay. Again, no, this is just to show you the complicated nature of the state space that you use for quantum computing. Okay, and essentially this reflects what Preskin was saying that there's a no the resources that you have in the correlations of quantum states, okay, are enormous, exponential. Okay, so this sort of reflects what's given there. By the way, this one, even at this stage, we do not know how to use this because essentially when it does this kind of thing, one talks about relative phases of qubits. And it would be wonderful to know how can we actually utilize the results that we find. So this particular paper that does not get cited by others, so probably not interesting enough. Right. The other ingredient part is the quantum logic gates. Again, just like the case of the qubits, you probably will not want to know about the whole SU2, or SU2n, essentially SU2 to the power of n, if you have n qubits, okay? So this is again, you have a continuous set of possibilities. You probably will not actually use that. So in fact, what people look for example, is to look for a universal set of gates. Okay, and this universal set of gates are usually a discrete quantity of gates. Okay, so for example, even this is not is quite large here. Okay, here you talk about CNOT gates, and then you talk about possible discrete elements of the SU2. Today, they found out that, okay, what one needs is a CNOT gate. CNOT gate is a 2-qubit gate, a Hadamard gate, and then you have this, I think they call it T gate or something like that. So that would be a universal set of gates for which you can actually implement discrete operations of those to actually realize a physical operation that you want to do. Okay, so normally people talk about all these possible quantum logic gates to be acting on this set of qubits, for example, and you apply these gates either in this case, for example, this is called a Hadamard gate. The Hadamard gate takes the computational basis and goes into a particular superposition. And then you can have things like the control knot is, for example, is a 2-qubit gate. So it sort of cuts across two qubits. Okay. So in a way, you need 2-qubit gates at least to have your qubits to be entangled. Okay. There was a work done by my joint PhD student. I'm not sure he's here. Siti Munira was actually able to generate all the known 3-qubit states by just having a set of 1-qubit gates and a 2-qubit gates. So you don't need the continuous collection of SU2n kind of operators. Right. I think I'm running out of time, so let me just move on. So what's the fuss? Okay, about Shaw's algorithm. Okay. Oh, I've forgotten to mention that this is a figure I pinched from Wikipedia, which actually implements what you call the Shaw's algorithm. Here, QFT is not quantum field theory; it's quantum Fourier transform. Okay. So you have a set of operations that you do on those gates. Okay. And then at the end of the process, you do some measurements. These are measurements. So this is what all this thing is called a quantum circuit gate. So what's the fuss about Shor's algorithm is the fact that today's, when you do online transactions in the internet, one uses some kind of public key crypto system. The most common one is RSA. And what is it based on? Again, there's typos here. What it's based on is actually the difficulty of prime factorization. Okay, so you have a large number. You know how to multiply two numbers together easily, but trying to factorize them is a bit, it can become computationally hard. Okay, so in fact, RSA laboratories actually post this RSA factoring challenge. Okay, this is you can find on the Wikipedia in superscript. I was doing this in a rush before this talk. They post to they made this challenge, open challenge to anyone to factorize their large RSA numbers. Okay, and the largest one, and this challenge has already been closed. Okay, and the largest number solved was RSA 768, which gives you a 232 decimal digit number. Okay, and somebody has actually solved this. Okay, and this is Kleinjung. I'm not sure how to pronounce that. And the kind of computational time that it needs is about 2,000 years. And this computation is based on the best known factorization algorithm that people know, which is the general number field sieve scheme. And it's the algorithm itself is essentially exponential of this number. Okay? B is your number itself in terms of bits. But Shor's algorithm sort of reduced this complexity of this computational to a polynomial time. And but in order to demonstrate this Shor's algorithm, you need a quantum computer, of course. But there's not one of useful quantum computing that can actually do it. You can do it for a small composite number, but not for a large one. So there is this paper recently by Gitney and Mosca who estimated if you want to factorize 2048-bit RSA number, you can do it with Shor's algorithm in 8 hours. Okay, but you need about 20 million noisy qubits, which is of course out of reach. The NISQ is probably just around 100 at the moment. I don't know. I'm not sure what's the most noisy qubit that people have now for the quantum computers. Okay, so this is possibly out of reach. Okay, and what am I supposed to say? Yeah, there was already a warning, made by, I can't remember the body itself, but they will say, okay, you might not need to worry about your security of your internet transactions now, but you probably need it after 2030. So they were already optimistic of what's going on with quantum computing. Okay, or afraid rather than optimistic. Okay, so that is talking about all the developments that have been there so far, and also some ingredients of what's there in quantum computing. So let me just say this quickly. The sad thing today is that we don't have a national program on quantum science and technology, despite I think several attempts. I think that we have not come to the point where we have a national program to say, in a concerted effort kind of thing. We have all these groups Okay, over here, I know more about UPM, so that's you can see there's a lot more here. But the rest, again, UM, you have people like Raymond, Prof. Raymond, and then recently, no, I did not know this before. Prof. Siti is now doing some kind of quantum walks. I know Dr. Bari in UKM, IIUM, of course, we have Dr. Jasny, who's doing a lot of quantum communication and QKD. And Unimap, recently I just get to know them. They had a LRJS project on quantum communications. UTM, I know Dr. Yap is here, so he's doing something on quantum computing, or no, aspects of quantum computing. Please correct me if I'm wrong. And then we have people in USIM. We have the I think the Vice Chancellor is Prof. Rsa, and then we have Dr. Siti Munira, the student I mentioned, is joining USIM. So we have people interested in quantum computing, and Prof. Rsa is actually doing quantum optics. The sad thing is that most of us are working individually, individual groups, and there's no real correlation between the groups. Okay, so we probably need some kind of a national program to see, okay, what can we do as a nation as a whole. So hopefully with people like Dr. Yap can do that in the future. Our current strategies are just to continue our efforts for critical mass, because we don't have that critical mass as yet. That's my personal opinion. So because of that, we cannot work in competitive areas too much, or fast-paced areas. So I would look for areas that has long-term goals and also less competition. And my personal options over here, well, at least we are not doing that properly as yet, but no, it's possible for us to pick this up, is to do quantum error correction. I'll mention why in a minute. And then we have categorical quantum mechanics, which could provide this so-called high-level language for quantum computing. Okay, so let me go into quantum error correction. So as you know, in order for us to have a fault-tolerant quantum computing, we need to have some kind of quantum error correction schemes. But most of these are not practical enough for to be implemented. They have been implemented experimentally, but probably not enough to do a large scale one. Okay, so the complications are coming from decoherence. Okay, and then also there are if we are able to copy qubits, then we can just have a repetition of copying the qubits. But one has this no cloning theorem, okay, that as sort of one cannot actually use multiple copies of them. Okay, so and then you have also this idea of the different types of errors that can come. Okay, not just the bit flips, but you also have the phase flips. Okay, for example, things like your superposition over here can be flipped in terms of phase in this manner. So that gives you a different quantum state. So one needs to protect against all these qubit errors, and one really needs a simultaneous corrections of those. Okay. So there have been schemes using stabilizer codes, which is proposed by Gottsman earlier, as I mentioned. And then later on, we talk about there are proposals about using these magic states. And there have been actually implementation of the on a small scale qubit thing to do this as a preliminary steps for fault tolerant universal quantum computing. Okay. Okay. Why we are interested in this? Because there are papers recently, or not so recently. The earliest was actually in 2014, but this was actually done by mathematician Lubotsky, that suggests that one can actually use the idea of hyperbolic manifolds, tessellation of hyperbolic manifolds to do the quantum error correction schemes. So that was interesting in the beginning. I thought, okay, when I saw this, okay, this looks fun. But then later on, there are more papers coming up. Okay, recently this by Lavasani Zhu and Bakashni talks about this dent twist and things like that. This is coming from their paper. Okay. So one needs to know about the idea of tessellations on the hyperbolic surface, which we have some experience in. Okay. We have been doing, for example, I believe Chan is here, we have been doing tessellations of hyperbolic spaces before when we try to study about quantum bound states on hyperbolic surfaces. So we have done this. So we have some experience to look at what groups usually this is called Fuchsian groups, okay, and how to tessellate using these Fuchsian groups. Okay, so we have that piece of knowledge that could have been actually used to include in this quantum error correcting schemes. But of course, this is this is different from what we do. Of course, this is the work of Chan. Okay, what about the other option that I mentioned? Just give me a few more minutes so I can finish this off. Is the idea of categorical quantum mechanics. My initial interest in this is not so much in towards quantum computing per se, but more towards from quantum foundations point of view. There was this idea, why is Hilbert spaces necessary? So even von Neumann was reported to say that when after he published his what you call book on quantum theory, okay, mathematical foundations of quantum theory, and then sort of say that he doesn't believe in Hilbert spaces anymore. Okay, so people have been trying to see how can one build quantum theory using other mathematical structures, and perhaps it's not the first time, I suppose, people have looked into category theory within the computer science school, but this one comes from Abramsky and Cooker. Okay, and Abramsky is a computer scientist, and Cooker comes from a quantum logic school. So this has already, having done some quantum logic and then probably seen developments in category theory, so they come up ways of being able to rebuild quantum theory using category theory. Okay? Category theory is a very abstract set of mathematics that probably needs time to actually master them. Okay, so the other thing that also happens is that all these category theory are actually essentially using the abstract idea of mappings, and inside maps, and these mappings will have certain you can see certain features of it that seems to be replicating in different branches of mathematics. So they start to figure out, okay, there are ways of using this as a category theory, the abstract notion of category theory. And then there's two, I didn't put it down, okay, probably. There are, okay, even the numbers are wrong. Okay, never mind. There are two mathematicians, Ross Street and can't remember who the other person is, the Joyal, who actually was able to describe all this category theory kind of using mappings, but instead of using just mappings, they have a pictorial way of using those the description of these processes. Okay, so Bob Cooker has started to adopt this and started to build a theory which is based on pictorial diagrams. And one of the things that probably it gives you some things that you probably have known in the past. You think of Feynman diagrams. Feynman diagrams become a calculational tools for quantum field theory. So over here, what happens is that some of the things that people do in this Hilbert space kind of computation gets simplified. Here is the case of a quantum teleportation. Okay. Now, if you remember how to do this, you can look up Nielsen and Chuang. You do all these different set of gates or set of logic operations, and essentially, in the end, they are really related to all these topological moves. Okay. So, and this one is actually from entanglement swapping. So all of this can be, instead of writing down things in Hilbert spaces, one can actually replace this by diagrams, and you can think of this as information flows. So remember, we mentioned about high-level language before. So having to know how the information flow actually helps you to design algorithms in some way. And probably after that, kind of calculus was actually developed called the ZX calculus, which is really coming from the polymatrices, okay, sigma Z, sigma X thing. And they developed this kind of language, and currently is actually being used in certain realistic quantum computing. If I'm not mistaken, Bob was saying that for that, but essentially ZX develop different algorithms, including so where our Akira, I'm not sure whether she's here today, but she did some work and graduated. Hopefully, she gets to publish the paper. And her external examiner is Bob himself, the pioneer of this ZX calculus. Okay. By the way, let me just announce, I promised to announce this to Dr. Nurisha, that Bob is coming to give our public talk on the next sequels on the World Quantum Day, which is 14 April. Is that right? Dr. Nurisha, are you here?
Yes, 14th of April.
Yeah. So he has already agreed to give a talk, and I already asked him to hopefully say something on this and real world implementation of ZX calculus. Okay. It's now in the industry. It's now in Cambridge quantum computing. Somebody asked a question here?
Oh,
Because
no,
I
no,
can.
it was just me clapping.
Okay, so okay. No. Sorry, I cannot see you guys while I'm presenting. So okay, so that's more or less the things I want to say. Oh, here, okay, here is the application of ZX calculus. So you can see that here's a circuit diagram that you normally see, and it gets translated in terms of ZX calculus over here, which you think that, okay, that's not much of an improvement, but we have all these rewrite rules in the ZX calculus, and you can actually simplify from this picture to this picture. This is a good place to start to learn about ZX calculus. Okay. So my speculation is that in the future, if one wants to find quantum algorithms that's probably exponential in the speed up, one has to really understand uh, uh, the global features. Remember, I talked about the Deutsch algorithm. Okay, is the global feature that actually stands out. Okay, so there are speculations that probably this is the kind of thing that we should go into. So I think that's it for today. I should thank Prof. Kuru for pushing me to do this survey. But no, I was the odd one out in the conference. And then I had some discussions with Prof. Quack. And then, of course, the work is probably supported by FRJS. Okay, that's all from me. So I should return to you. If there are questions which hopefully I can answer, because I'm not the expert inside this area, so probably Dr. Yap can actually help me out. Okay, any questions? So probably not, I suppose. Again, I apologize for the sketchiness of this talk, because I couldn't get into the details, without making it as a series of lectures, which I don't know. I don't think I can do that at this stage. Any questions? Nope. What's the next breakthrough in algorithm? I don't know. I was hoping that the non-abelian hidden subgroup problem, because that would actually help solve the graph isomorphism problem. But I don't think it will be in the near future. Probably not. People take years to understand this. Any other questions? Or should I turn off the recording now so that we can have an informal session? Okay, I guess not. So thank you everyone for listening. So I will end this recording now.